The Google search engine has two components, searching and ranking. Searching is around the text mining, and for ranking, Google has the PageRank algorithm. In this section, we'll consider text mining. It's about searching. Text mining is a method that extracts useful information from large and unstructured collections of texts. A related term is information retrieval. A typical application is a search in databases of abstract of scientific papers. For example, in medical applications, one may try to find all the abstracts in the database that is dealing with a particular syndrome. So one can put together such a phrase as a query with the keywords that are relevant for the syndrome. Then the retrieval system is used to match the query to the document in the database, and result can be made to the users, and users can see all the documents that are relevant, preferably ranked according to the relevance. Let's see this example. The following is a typical query in medical applications. The use of induced hypothermia in heart surgery, neurosurgery, head injuries, and infectious diseases. Okay, for this query, we will refer as Q9 in the following. So that is the name to be Q9. Another well-known area of text mining is web search engines. The search phrase is usually very short, and it's often the case there are so many relevant documents that it is out of the question to present them all to the user. So that's reason ranking is quite important. But in that application, the ranking of the search result is critical for the efficiency of the search engine. So we'll consider this aspect in the next section. Now we'll focus on searching, the text mining. There are many public domain text mining software. And here we have two typical software freely available. In R, TextMine R is available. In Python, here we have Natural Language Toolkit, NLTK, and Spacie. That is written in Python. Python is, in a sense, another language between C and Python. And Python itself is so slow. And once you try to implement the core algorithms, core operations in C, and the compiled object is used in your the simulation wrapped by Python, then it is way faster. You can enjoy, in most cases, about 100 times faster. However, many Python users are not familiar with C, so that it's between C and Python. And so if you understand Python, then now inside of Python, you can easily manipulate. Once this Python was quite popular, but nowadays not much. And anyway, in Python, spacing is available for text mining. In this section, we'll consider text mining techniques, and one of a very common technique is called vector space model, because it is dealing with like a vector and metric computation. So in the last section, in fact, section 13.2, the first example, and we demonstrated the basic ideas of the construction of the term document metric in the vector space. And we try to consider first some pre-processing, and then and later on in the second part of the section, we consider a variant, so-called latent semantic indexing, which is using singular value decomposition and using some smaller number of bases so that we can get sometimes better results. Okay, let's see here. The pre-processing and query matching. In information retrieval, keywords that carry information about the contents of a document are called terms. And the basic task is to create a list of all the terms in alphabetical order, and now that's called index. And before the index is made, we have to do a little bit of pre-processing, some non-necessary or appearing in many cases, then it has no specific meaning, so that sometimes some word must be eliminated. Also, some words must be now trimmed to get their stem. Okay, let's see here the example. Removal of stop words. Stop words are words that can find in virtually any document. For example, or, able, about, above, and so on. Such words are appearing everywhere. So eventually, it has no specific meaning. So we will try to remove these words. And we call them stop words. And now there are various the stop words removal, the list of these words, and one of them can be found over there. Just the algorithm, some later on, the algorithm will use these stop words so that if you put a word inside these stop words, then it's automatically eliminated. Now, stemming is the process of reducing each word that is conjugated or has a suffix to its stem. Let's see these words: computational, computation, computing, computed. Oh yeah, that is computable. Okay, I'm sorry. And computational, then the stem can be here compute. So either you write computable, computation, inside in the search engine, compute will be used there. And also, this stemming operation can be done quite easily, and the algorithms are well established. And from some internet, you can find the algorithm freely. Here, one example is here, photo stemming algorithm. You can get the algorithm from the website. Now, we go back to the term document metric. the term document metric has dimension n by n, then m means the number of terms in the dictionary. You saw earlier in the last section, the terms in the dictionary, the terms are alphabetically ordered. So there are m terms, and n is the number of documents. So n is practically the number of websites. It's common not only to count the occurrence of terms in documents, but also to apply a term weighting scheme. Let's see this example. And anyway, the document and term weighting is usually done. For example, one can define the element in the metric A. Okay, let's okay, A is the term document metric. Then Aij can be given in this way. Earlier, we considered only frequencies, and frequency is given in the metric. Now, rather than frequency, we give some weight. So that is here. In fact, this quantity is now negative of logarithm ni over n. So the ni over n is the portion, and ni is the number of documents that contain the term I, so that the reciprocal, but in fact it's a negative of logarithm ni over n. So the one says, so eventually it becomes the logarithm of the inverse document frequency is used in this formula to give some weight. If a term occurs frequently in only a few documents, then both factors are large, so that eventually this will be very large when it's appearing only a small number of documents. In this case, the term now discriminates well between different groups of documents, so that here, along with a large weight, the small number of documents will be well detected. So weighting makes the algorithm more effective. That's the idea. This is one example of weighting. Okay, normally the term document metric is sparse. That means that most of the metric entries are equal to 0. And for the stemmed MathTalent collection, there is a kind of a medical application, so that some syndrome, along with the syndrome, some papers are collected, and then now along with some query, try to find. So abstract search and try to find the relevant papers. That's the purpose of this MathTalent collection application. Okay. Now the metric has this size. That means that there are more than 4,000 terms, and now having now more than 10,000 papers, and with among them here only non-zero entries as only this one. So that is only about 1% is non-zero. And here, and this figure is showing that the first 500 rows and columns of the metric, and as you can see here, mostly empty. Yeah, dots are just the non-zero numbers. Okay. Now here in query matching, now we have the term document metric. And once you make a query, then query will be again represented as a vector. The length is the same as the number of rows, so the Q will be in RM. The queries are parsed using the same dictionary as the document, so that it will become a vector Q. And now query matching is the process of finding all documents that are considered relevant to the particular query. And this can be done using the cosine distance measure. Cosine distance measure is quite popular measure. The measuring between two vectors is a similarity. Once they are the same direction, then the value will be around 1, but it's far away, like 90 degrees, then the value will be 0. And opposite direction, the value can be -1. Now, because it's using frequencies so that the values are positive, so that, and here the smallest value will be around, for example, 0, and then largest one will be 1 anyway. And all for all documents, here we are measuring that, and which means that each column represents a document. For each document, we are trying to measure the cosine distance. So once the cosine distance is larger than a tolerance, TOL, then that is considered as the relevant document. Okay, let's see here. The query matching is performed for the query Q9. Earlier we defined this query here. Okay, the query, oops. Oh yeah. Okay, that one. In this example, we call this query as Q9, and this MathTalent collection. For the MathTalent collection here, okay. Now, when we choose tolerance 0.19, then only a single document is considered relevant. Only one document is found. And once you choose a little bit smaller number, 0.17, then 3 documents retrieved. So depending on your choice of tolerance, this output, so satisfying the columns, which means satisfying this quantity, which means that now the documents, and because AJ is representing the paper document, so that anyway, depending on your choice of tolerance, and many of AJ can be selected. And here, so we have to have some guideline or standard such that once you design a new text mining algorithm, then we have to be able to compare your new algorithm and the old algorithms. In order to do that, we need a little bit of now definition. Okay. Now, let's see this one. An irrelevant document may be returned for high value of the tolerance. If you choose the tolerance large, then the retrieved documents are likely to be relevant because only small number will be collected, selected, and maybe more likely the relevant. When cosine tolerance is lowered, then more document will be chosen, so that irrelevant document may be returned relatively more. It's quite natural, the thinking. And here we define two terms, precision and recall. In performance modeling for information retrieval, we define these two terms and use quite frequently. Here, precision is defined in this way. Okay, over there, capital T means that there's retrieved. So the total retrieved, so that all retrieved papers, among them, the relevant one, the ratio is called the precision. Now, capital B means the document in the database. So now that is only for the relevant documents. Now, from the all document in the database, here we try to measure the portion, the retrieved. So that is called recall. Here, now we do a little bit of a mind simulation. Okay. Now, we see that with a large value of tolerance, we have high precision. That's exactly this one. Once tolerance is large, then relatively the retrieved documents are likely relevant, so that eventually we have high precision. Right? However, there is low recall. You may consider this one also quite easily. And for small value of tolerance, we have a high recall, but low precision. That's the opposite of this statement. So that now, along with this MathTalent collection, and also along with the query Q9, and we try to choose variants, the many tolerance, and for each tolerance, we try to find the precision and recall. And we try to make this diagram. For example, once you are choosing small tolerance, then that will make, okay, over there. If you are choosing now small tolerance, then we have high recall and low precision. So that means that this area is along with low tolerance. If you are increasing the tolerance, then and later on you will make that one, and again this point, again that point, and so on. So that this is the smallest case for the tolerance and high recall and low precision, and along with a little bit larger tolerance, you have this the recall and precision. In this way, we can make this diagram that is called recall versus precision diagram. So for given algorithm, you can make this recall versus precision algorithm. However, the goal is, and we have to have larger precision, larger recall, so that eventually, if you have better algorithm, if you design a better algorithm, then and you can test your algorithm along with various tolerance, then your curve will be here around there. So that the curve is near around right upper right corner, then near to the this corner, then the algorithm is better eventually. So it is quite useful and visualizable the tool for the comparison of algorithms. So along with the definition of recall and precision, we can see the performance of the text mining algorithm. Okay, that's the first part, and we'll continue in the second part. Thank you.